Well, we made it. This is our final lesson covering new information. And it's technically not new information. It's continued from the last lesson, but we are definitely going to do this in the context of an AP type problem. I've got a couple of examples here we're going to go through. And that's it for new information. That's it for series. You made it. Congratulate yourself. Pause the video. Pat yourself on the back. You've done a great job. We will have additional videos, but they're just going to be housekeeping videos covering our practice exams after we take our series exam when we get back from spring break. So this is it. So here is an AP type question. It says the Maclaurin series for the function f is given by this function f. They give you the general term and they give you the first four non-zero terms on its interval of convergence. Part A says find the interval of convergence of the Maclaurin series for f and justify your answer. Well, we just learned in the last set of videos how to do that. And so that comes from starting with a sub n, which is 2 times x to the n plus 1 over n plus 1, finding a sub n plus 1, which is 2 times x to the n plus 1 over n plus 1 plus 1. And so we plug that into our limit to run our absolute ratio test. And this cleans up to 2x to the n plus 2 over n plus 2. So that's what we'll put in here. That's 2x to the n times 2x squared. And then we'll have all of that over n plus 2. We have the reciprocal. I don't know why I want to keep writing 2n. 2x to the n times 2x to the 1. And then all of that was over n plus 1. So let's clean our limit up for large N. Those things are going to cancel. Algebraically, we lose one of those to that. So this result looks like that. That's all that's left in that limit. As n approaches infinity, 2 times x is a constant. We are going to converge where that is less than 1. We can expand that. Please don't forget to drop your absolute value marks at that time. And now we need to divide each piece by 2. So there is where we are. That is the portion of our interval of convergence. And now we need to find out what's happening for x equal negative 1/2 and find out what's happening for x equal positive 1/2. We're going to plug that into our general term. We started n equals 0 to infinity. We have the quantity 2. And I'm going to plug in a negative 1/2. And that is all raised to the n plus 1 over n plus 1. So we clean that up again. And we get negative 1 to the n plus 1, because 2 times negative 1/2 is negative 1. That's all I've done there. And this is an alternating series. So we're going to run the alternating series test. The limit as n approaches infinity of the positive portion, that does indeed go to 0. 1 over huge is tiny. This converges by the alternating series test. So there's our left endpoint. It is included. And then we'll come back over here for our right endpoint. And we'll show the AP reader that when we plug in a positive 1/2, that this cleans up to a positive series. Now this has a value of 1. 1 to the anything up there is just 1. So this is a positive series that, once again, just like our last examples on our last set of videos, we could run the limit comparison test here. B sub n, we'll use the harmonic series. We need to show we recognize this is the harmonic series. Notice when I recognize it's the harmonic series, I actually write it as a series. I don't just do that with the B sub n term. So this is the harmonic series, which we all know diverges, so we just get to say that. We're going to plot this in the limit and run the limit ratio test, limit comparison test. So the limit as n approaches infinity, we get 1. That's an excellent result. So this diverges by the limit comparison test. And our answer to the question is and did they call it convergence set or interval? Interval of convergence. The interval of convergence is, we'll extend the page here, we went from -1/2 to 1/2. We found out that the left endpoint is included while the right endpoint is not. So there's our interval of convergence. So that would be part A of a free response question. That's exactly what our work would look like, so you see why we did that practice before. Here's one. Say this is part B, same question, same series. Part B says find the first 4 terms and the general term of the Maclaurin series for f prime of x. And this is why when they ask us to find the general term, we're generally just asked to find the derivative of it. This is what that would look like. I don't know if you remember on the set of lessons where we talked about operations on power series, and I told you we're not very often asked to integrate that general term, but we are often asked to differentiate it. So if this is f of x, then I'm going to show them that I recognize f prime of x is going to be the derivative. Now I'm taking the derivative with respect to x. That means the power pops down front, right? Reduce the power by 1 times the derivative of what's inside, and then this is just a constant as far as x is concerned. Okay? So chain rule, power rule, all that comes into play. Now I just differentiate term by term. The derivative of 2x is 2. The derivative of 4x squared is 8x divided by 2 is 4x. The derivative of 8x cubed, that 3 pops down front. It's going to cancel with the 3 that's already in the denominator, and that's going to leave me with 8x squared. Same type of thing happening in the next term. The 4 is going to pop down front in my power rule, cancel with the 4 in my denominator, and I'm going to wind up with 16x cubed. And I've already shown them the general term, but if you wanted to, you could include that here as well if you wanted to. But this is what the general term is going to look like. Don't forget your chain rule. There we are. Okay, so there is our answer to part B. Let's see what they ask us to do on part C. Use the Maclaurin series you found in part B to find the value of f prime. All right, so I'm just going to copy down again what we found here. We found plus 4x plus 8x squared plus 16x cubed I'm not going to pull in the general term here unless I feel like I need it. If I feel like I need it to answer this question, then I'll pull it down and we'll fiddle with it if we need to. So there's f prime and x. They want me to use this infinite series to find the value of the function at 1/3. So everywhere that there is an x, I'm going to write a 1/3. Here's the problem. I've always said, hey, all you ever have to do is just plug in a number. If you get numbers, you're done. We're not done here. When they say that they want you to find the value, they don't want it inside of a power series. Or in this case, they don't want it inside of a regular series, just a general series. Here's a series of constants. But we still haven't found what the value of f prime of 1/3 is. So here's something that I know. I know when I'm dealing with a power series, I'm dealing with a geometric series. Remember, we talked about that. And the power to that is, if I can identify A and R, I can find the sum of that series. So I want the sum of this series when x is 1/3. So what I need to try to do is to get this into the form where I have A plus A times R plus A times R squared plus A times R cubed, and so forth. And that's going to let me recognize A and R. Okay? Well, I recognize that each of these terms has a 2 in it. So I'm going to factor that 2 out. Then let's see what we get here. That'll be 4 times 1/3 squared. That'll be 8 times 1/3 cubed. And that turned out to be a really good plan, because look what's happening for me on my coefficients. They're all powers of 2. So let's rewrite this as fractions. This is 2 squared times 1/3 squared. Couldn't I just write that as 2/3 squared? And then the next one is 2 cubed times 1/3 cubed. Wouldn't that just be 2/3 cubed? And look, I don't need the general term at all. 2 times the sum is going to be 1 over 1 minus r. That's what the sum of this series is going to be. That's going to be the output of the function at x equal 1/3. Now we could go ahead and clean that up. We wouldn't have to, but it looks like that's where we're going. 2 times 1 is 2. 1 minus 2/3 is 1/3. This is 6. And it probably wouldn't be a bad idea to show the AP reader that. So there we are. Please don't forget the 2. The 2 is part of the sum. But I factored it out front to kind of get it out of the way so we could see what was going on with A plus A times R and so forth. So there's an AP problem. Not difficult, but in this context, they can ask you to do a lot of things with your series, not just find the convergence set and not just talk about error. There's a lot of things they can ask you to do with your power series. They can ask you about maximums and minimums. They can ask anything they can ask you about a function. They can ask you concerning a power series. And the fact that we have infinitely many terms changes our work just a little bit. Now I have one more example that I'm going to get started on. We won't be able to finish it. As a matter of fact, I think we're close enough to the end of this video. We'll just stop right here, and a second video will cover this second example. So watch for the next video.